Hello, welcome to Reality Part 3. Let's start with a quick recap of what we said so far. So we said that the property or charge values are held by the points of the elementary particle's world line. And in our case, we will use world lines that are called Jill, Jack, Alice, and Bob. The charge, and in our case we'll use a charge on the world line called Alice, creates a field along the information track that goes through the point holding the charge. And in our presentation, the field is created in the up direction. So if we look at this point on Alice, it is part of a world line, which means that it has charge values. There are information tracks that go through this point, and the charge values create a field along these information tracks in the upwards direction. This means that if we look at the point over here on this information track, it has field value numbers that are correlated to the charge value numbers at this point on Alice. We also said that the field values decrease at points further along the information track from the source, which is the charge. And finally, we said that the field affects an elementary particle by changing the trajectory of its world line. So if we look at this point on Jack, it has charge values and information tracks that go through this point. So it creates field values along these information tracks in the upward direction. And if we look at this point on Jill, it has field value numbers that are correlated to the source, which is the charge values at this point on Jack. And the same goes for this green point over here on Alice. It has field value numbers that are correlated to the source, which is the charge values at this point in Jack's world line. However, the field values in these 2 points are not the same because, as we said, the further you are along the information track from the source, the weaker the field is. So the field values over here are smaller than the field values over here on Jill, which is closer to the source along the information track. And finally, we said that the field values affect the charges by changing the trajectory of the world line. So if we look at this point in Bob's world line, it has Bob's property values, and it has field values that affect these property values by changing the trajectory of the world line from this point to the next point along the world line. And if we look at this point over here, the same. It has Bob's charge values, and they're affected by the field values by changing the trajectory of Bob's world line from this point to the next point on the world line. In this video, we will elaborate about the effect of a field on an elementary particle, add a distinction between a charge and a field, and explain why the field values decrease at points further along the information tracks from the source. But before that, a few things to notice. The first one is that the description we are using here is a classical way of looking at charge and field. However, currently, the way physicists treat this realm is with quantum mechanics. So this description of classical way is not the best one we currently have. Nonetheless, the theory of relativity was conceived with a classical way of viewing the world, and therefore it works with it in mind. And this means that Einstein's theory of relativity does not necessarily work with a quantum mechanical view of the world. And indeed, trying to reconcile general relativity, which is a reality with gravity, so trying to reconcile it with quantum mechanics is one of physicists' main quests in this day and age. We will also consider that relativity was conceived with two known charges in mind: the electrical charge and mass. However, as we mentioned, we are starting with a model of a reality without gravity. So this means that for now we are left only with the electric charge and the electric field. In this depiction, the world lines are straight lines, and this is a representation of a case where we turn off the effects of fields on charges, and then the world lines are straight, with the idea that as the effects of a field on a charge is to change the trajectory of a world line, once we turn this effect off, the world lines do not want to change their trajectory and therefore continue in a straight line. So we can say that the natural form of a world line from our outside perspective is a straight line. And this is Newton's first law. An important thing to add is that the value of the mass property tells us how much the path wants to stay straight. So the mass of an elementary particle captures how much it resists changing from a straight line. Now let's try to understand how the field changes the trajectory of a world line. So if we look at the electric field at the elementary particle point we examine, and we will use Bob's world line for that, it wants to change the trajectory of the world line to the information track it traveled along. And this happens when the signs of the electric charges are the same. So if we look at this point on Bob, it has the electric charge of Bob, and it has a field, an electric field that is created by the electric charge of this point on Alice. If both electric charges are of the same sign, so two pluses or two minuses, then the effect of this electric field on the electric charge of Bob at this point is to want and change the trajectory of Bob's world line to the information track that the field was created along. But if the signs of the electric charges are opposite, then the electric field wants to change the trajectory of the world line to the opposing information track it traveled along. So again, if we look at the same point, but in this case we say the electric charge of Bob and the electric charge of Alice are of opposite signs, so one is plus and one is minus. And in that case, the field that is created over here by Alice's charge affects Bob's charge by wanting to change its trajectory to the opposing information track that it was created along. So in this way, it wants to change the trajectory in this manner. Now the value of the electric field combined with the value of the electric charge held by the elementary particle, which is in our case Bob, tells us how much it wants to change the path. And the final trajectory of the world line will change according to the balance between its desire to stay on the one hand in a straight line, and that is determined by the mass value of Bob, and its desire to move along the information track that the field dictates. And that is determined by the value of the electric field combined with the value of the electric charge held by the elementary particle it is affecting, which in our case is Bob. And this is Newton's second law. So the scenario we're looking at over here is that up to this point on Bob, we turn off the effects of fields on charges, and at this point we turn them back on. So at this point we have a field that is created by the electric charge of Alice over here, and it affects the electric charge of Bob at this point. And we will say that they are of the same sign, so two pluses or two minuses. So the trajectory of Bob will change from this point on according to the two desires that it has. On the one hand, it has a desire to keep on going in a straight line along this gray line over here, and the measure of this desire is captured by the mass value of Bob. The other desire is to change the trajectory to this information track over here, and the measure of this desire is captured by the strength of the field combined with Bob's electrical charge. And according to the strength of these two desires, the trajectory will change from this point to the next point on the world line. Then again, the next point will have a field and a charge, and again we'll have two desires that will affect its trajectory and will change the trajectory to the next point. And so on. As you can see, the trajectory from here on keeps changing. However, it is a little bit more complicated than that, because the electric field at the elementary particle point that we examine, and in this case we'll use the world line called Alice, is a combination of all the field values traveling along all information tracks. And this combination of all fields gives us a value and a direction. The direction tells us about the path to which the field wants to change the world line, and this direction is a combination of the different directions of the information tracks that bring the fields, but this combination is weighted, so the information track with a higher value of a field has more weight to its direction. And the combined value tells us about the strength of this desire. The strength of the desire is this combined value combined with the value of the electric charge held by the elementary particle itself, which again in this case we will use the world line of Alice. So if we look at this point on Alice, it has Alice's electrical charge, and this electrical charge is affected by two fields. One is created by the electric charge of Jack at this point, and one is created by the electrical charge of Bob at this point. Let's start with Jack. So this electrical charge on Jack creates along this information track a field, and we'll assume that the electrical charges of Jack, Alice, and Bob are all of the same sign, so all pluses or all minuses. So this means that the field created by this point on Jack affects Alice's electrical charge at this point by wanting to change its trajectory along the information track it was created. So in this manner. And now if we look at Bob, then this electrical charge of Bob over here creates a field along this information track, and it affects the electrical charge of Alice at this point by wanting to change its trajectory in this direction. But as you can see, I depicted this desire in a thicker line than this one, meaning that the field created by Bob is stronger than the field created by Jack at this point on Alice world line. And the final field direction is a combination of these two desires to change the trajectory of Alice. So as you can see, it wants to change Alice's worldline trajectory in this manner, a little bit more to the left towards the stronger field created by Bob's electrical charge. And the final trajectory, and again, we're talking about a scenario that up to this point, we turned off the effects of fields on charges, and at this point, we turn them on. So at this point, we have two desires. One desire is to continue in a straight line like this, and the measure of this desire is captured by the mass value of Alice. And we have the second desire, which is to change the trajectory along this line over here. And this desire is captured by the combined field value of both the fields created by Bob and Jack at this point, combined with the electrical charge of Alice. And according to this balance from this point onward, the trajectory will keep changing. Now, if we look to a point in reality that is not part of a world line, then again, the field values at that point are the combination of all the fields going through that point. And again, the combination gives us a value in the direction. The direction tells us about the path to which the field wants to change a hypothetical world line. And the value tells us about the strength of this desire. And the strength of this desire is the combined value of the field combined with the value of the electric charge held by a hypothetical elementary particle. So if we look at this point over here, it is affected by two fields. One is created by the electrical charge of Jack at this point, and one field is created by the electrical charge of Alice at this point. And the process is the same. The final field direction is a combination of these two directions, with the higher field value having more weight in deciding the final direction, and a combined value of these two fields, which tells us how much a hypothetical world line going through this point would want to change in the direction, in the final direction of these two fields combination. So the process is the same as is in a point that is part of a world line. So the final field at this point and at this point are determined by the same process, the combination of the fields that affect these points. However, there is a crucial difference. Fields go through each other, but fields stop at a charge, at an elementary particle. So if we look at this point, it is affected by two fields, but they do not interfere with one another. So if we look at the point on this information track over here, its field value numbers are still correlated with this electrical charge of Jack. And the same for a point over here, the field value numbers of it are correlated with Alice's electrical charge over here at this point. So even though they are both going through this same point, they do not affect each other. But if we look at this point on Alice's world line, the field values that are at this point are swallowed into the trajectory change of Alice's world line. And if we look at the point over here on the information track at this point, then the field values of it are no longer correlated with the electrical charge of Jack at this point. The field values are correlated only to this point on Alice, to the charge values of Alice at this point. Also notice that a field has a direction because it follows an information track, and information tracks exist in reality. A property or a charge does not have a direction. The direction of the world line is determined by rules. So the world line wants to continue in its path with desired mass, plus it wants to continue in the direction of the combination of affecting fields with the desire of the combined field value and the corresponding charge held. So for example, if we look at this point over here on Jack, it has field value numbers, but these are combined with a direction. So the field has a direction. It wants to change the trajectory either along this information track or this information track. And this is different from the electrical charge held by this point that does not have a direction. Okay, moving on, let's try to find out why the field value decreases as it advances along the information track. And for that, we will use a three-dimensional flat reality model. And if we look at this kind of model, we see that the information tracks going through a specific point form two opposite cones. And these are called light cones. So here we have our three-dimensional model of reality, this three-dimensional cube. And we're looking at this specific point, the red point over here. And all the information tracks that exist and go through the point are all the straight lines that create a 45-degree angle with this vertical axis going through this point over here. The combination of all these information tracks create these two opposite cones. Now if we look at the top cone, and I will remind you that that is where the field is created, it can be described as circles, one on top of the other, with every additional circle being bigger than its predecessor. So something like this. We start from this point over here, the point holding the charge. On top of it, we have a small circle. On top of that, a little bit bigger circle. On top of that, a little bit bigger circle, and so on. So as we move away from the source along the information tracks, the circles grow bigger. And the idea is that the value of the charge is shared between a growing number of points, bigger and bigger circles. So each point holds less and less of the value, as it has to share it with more points. Now the number of points is captured by the circumference of the circle. And this means that the value of the field decreases as the growing of a circle circumference. So if we look at this point over here, and let's say it has a charge value of 10, then this value is held just by 1 point. And what we're saying is that if we look at a point over here, then this same value of 10 is shared along all the points of this circle. So it's not held by 1 point anymore, it's held by many points. This means that each point holds only part of this 10. And if we go further along the information tracks from the source, then this circle is bigger, meaning the value has to be shared by more points. And therefore, each point has a smaller value of the field. Now, if we look to the actual four-dimensional flat reality, we cannot imagine what is the form of all the information tracks going through a specific point. However, if we add a dimension to our circle description of cones, we can describe the form as spheres, one on top of the other, in an extra direction that we cannot see, with every additional sphere being bigger than its predecessor. So we add a dimension to circles and they become spheres, and we describe the form using these spheres just like we did with the circles and the cones. Now, using the same idea as before, that the value of the charge is shared between a growing number of points, a bigger sphere every time, leads us to the same conclusion that each point holds less and less of the value as it has to share it with more points. But now the number of points is captured by the surface of the sphere, not the circumference of a circle. And this means that the value of the field decreases as the growing of a sphere's surface. This means that the field decreases in value as it moves along an information track, depending on the amount of dimensions reality has. And this is Gauss's theorem. Okay, with that we finished describing reality. Reality is the solution to the rules that we presented, meaning that each point's numbers are the correct ones. So the rules that we described are satisfied. Now, the solution is complicated. Each world line's trajectory is affected by all other world lines, either directly or indirectly. And its trajectory affects back all the other world lines, either directly or indirectly. And also, let's not forget that there are two more dimensions for the world lines to exist in. This means that world lines are not restricted to a plane. The restriction to the plane is only in our presentation, and this is only for the benefit of the explanation. So even if we look at a simple example of just a few world lines, it is hard to imagine the trajectories and how they satisfy all the rules that we described. And it's extremely hard to imagine when we go to the actual reality, where we have a huge number of world lines affecting each other. But nonetheless, the individual rules are comprehensible by themselves. Okay, in the next video, we will begin our second part of the roadmap, the experience of the described reality.